Okay, looks like we're at the top of the hour. Let's go ahead and get started, everyone. Good morning or good afternoon, depending on your time zone. Let me start off by first saying thank you. We appreciate your time. I know that everyone's extremely busy these days, and for you to spend some time with us, we really appreciate it. Today, our joint webinar is hosted by Axellio, um, Garland, and Mira Security. Our topic is a fascinating one. We're calling it the TLS 1.3 encryption paradox. Are we strengthening end-to-end encryption, but also limiting our cybersecurity monitoring capabilities? So as we kind of some logistics, please feel free to, during the webinar, to drop any questions into the chat. We do have a team answering them as we go through, and we'll do our best by, at the end of the session to leave a little time to answer a few of those questions as well. So I'm joined today by two amazing leaders and experts in their fields. The first is David Wells. He is the founder and product and technology strategist at Mira Security. He has many decades of experience in networking, cybersecurity, wireless technologies, and standards development. Welcome, David.
Thanks, Scott. It's good to be here. It's going to be an interesting talk.
All right, thanks, David. Also joining us is Chris Beharry. He is the CEO of Garland Technology. Chris has over 20 years experience driving solutions for better visibility across network access. Welcome, Chris.
Thanks, Scott. And yeah, David, Scott, excited to be here today, and thank our audience for joining, and look forward to jumping into it.
Awesome. Well, my name is Scott Aiken. I'm the CEO of Axellio. I also have spent a couple decades in the cybersecurity space, both on the commercial and government side. So let's kick this off. I think that we'll probably all agree that secure end-to-end data encryption is essential to safeguard the information on our networks today. However, it creates a paradox. The same technology that safeguards our information can also limit our visibility into our cybersecurity solutions, our network monitoring tools, our analytics, forensics, and I could go on and on. To date, most organizations are generally able to monitor and analyze encrypted content that either originated or terminated on their network. For instance, with TLS 1.2, this was fairly easily achievable if you didn't have the forward secrecy enabled. But with TLS 1.3, this goes away. With forward secrecy, the default in 1.3, this will significantly change how our enterprises have to achieve visibility inside the network. It will require fundamental changes in the approach that you need to take to appropriately monitor the infrastructure. Something we really need to spend some time to walk through here. So let's set up the first question here for you, David. Based on your experience over the years building and implementing encryption technologies, why is decrypting traffic so essential for security monitoring?
That's a good question, Scott. I mean, as you say, there's been the ability to monitor encrypted traffic to a degree for a while, but the real change is the fact that pretty much everything is now encrypted, or everything that matters is encrypted. And TLS is the primary encryption mechanism, but it does a good job of doing two things, of letting the user be confident they're talking to the right server, so it gives authentication to the server, as well as encrypting the actual end-to-end communications you say. So the bad guys know that encryption's out there and they use it. I mean, 85% plus of threats these days come across encrypted channels. So they can hide the attack, and they can also hide the consequences of the attack. So if you do get penetrated and they're exfiltrating sensitive information, that'll be over an encrypted connection as well. So you won't see it with your normal security and monitoring tools, just they can't see inside the encrypted flows. So pretty much everything you're doing in or out is going to be encrypted, and that is good for the user, but it opens up opportunities for malign actors. The other point just to make is that a lot of organizations work in a fairly tightly regulated environment. So they may have regulators that place requirements on them to be able to prove that they're not exfiltrating customer data, for example. But if you can't see what's in the data that's going out because it's encrypted, it's really hard to comply with that sort of regulation. So I think, bottom line, you need visibility into the encrypted traffic if you're going to have a good security posture for the organization. And it's not just for security, but as you say, fault detection and resolution in network problems. If you're just looking at encrypted streams, is very difficult to achieve. If you can see what's inside them, then it's a lot easier.
Okay, that makes a lot of sense. So with the previous versions of SSL and TLS, and they've been around for quite a while now, we've been able to decrypt these protocols as long as we either had control of the server or the client. Is that correct?
Yes. So the way that TLS decryption works for any version of TLS, you either need to have some control over the server or some control over the client. And the control means that you can do two things. You can convince the user that you are the server that is really being talked to, so you can handle the authentication. But you can also get hold of the session keys for the session so that you can decrypt the user data. And really, the two techniques that are in use are dependent on which end you have some control over. So if it's an employee, if it's a customer coming in to talk to your server, you obviously control the server. It's easy to get a copy of the server's TLS certificate and its private key and install that on the device that's going to decrypt the traffic. And that means that for the user, it is the server. It authenticates very easily and you can decrypt. And with versions prior to 1.3, you could do that type of decryption passively. So you could, if you have the server certificate and key, you could work on a copy of the network packets and do decryption. That's what we call non-server key decryption. But the other use case is it's your employees inside the organization going off to TLS servers that are on the internet. They're going to Gmail or Facebook or something. And in that situation, we need to use a different technique to get visibility. Because the server certificate that comes back from Gmail is what the user is expecting to see. And in order to do decryption, we need to modify that server certificate and send the modified version to the user. But the user's browser would typically reject that and say it's not a trusted destination anymore, unless we install an enterprise certificate authority in the encryption device so that it can use that to sign the modified server certificate before it sends it to the client. And the client trusts the enterprise CA, so it trusts the modified server certificate. So that gets us over the authentication hurdle. But in order to do that, we obviously have to be in line because we need to modify the traffic between the server and the client. So for that certificate resign visibility mechanism, you always have to be in line no matter what version of TLS you're running. So hopefully that kind of gives some picture of how it works.
Got it. Thank you. So now let's head over to you, Chris. How have the TLS versions prior to 1.3 that did allow the passive known server key inspection influenced how we did our monitoring?
Yeah, absolutely, Scott. And so at Garland, if you're not familiar, so we get involved in making network taps, aggregators, packet brokers. And what we focus on is figuring out the best way to get copies of the traffic to your security and monitoring tools. So a lot of this, prior to 1.3 was, as we've been talking about, a passive listening mode for getting copies of traffic. So when we look at, putting together an architecture of getting traffic from a customer's network to their security and monitoring tools, we look at using technologies like network taps. So if you're not familiar with how a network tap works, it's a piece of hardware that you can insert between two network devices. So Scott, you and I are talking right now, and if we were to put a network tap in between us, the tap would copy everything you say and everything I say. So in the network world, let's say we place a tap in between your firewall and router. We would actually, the tap itself would have no IP address, would not be visible, and its whole mission in life would be to copy everything, all the traffic from the router to firewall and firewall to router. So by inserting a network tap architecture into your network, this would allow you to do some passive monitoring. And if you were looking at, say, maybe tapping, 10, 20 links at the edge of your network, we could take a copy of that traffic, bring it into one of our packet brokers, and from there we can feed it through a decryption device and be able to then share that traffic to one or multiple tools. So traditionally, the way we would approach it would be to look at where you want to insert your taps, packet brokers, and be able to get a copy of that traffic so you can decrypt it and then send it to your security and monitoring tools. Because again, it's important that your security tools get to see all the traffic. So, our tagline, "See every bit byte packet." So, excited to be here with Mira as well as Axellio, because I always like to say the truth is in the packet, right? So we have to figure out the best way to architect the network to be able to get this packet level data, so you can get full visibility. But traditionally, again, a lot of times we would be looking at doing design in more of a passive listen only architecture, and that's what a lot of people have been used to. And now with moving to 1.3, we do have to look at some other ways of architecting the network to be able to put it actively in line, and look at ways to be able to accomplish that, and also minimize network downtime. We want to make sure we put in equipment that allows you to have network uptime, deploy active inline devices to do decryption, because the passive mode, right? I think a lot of people were very used to deploying, right? They're very comfortable with putting in a passive network tap to be able to get the traffic off the network. And when you do move to 1.3, it does bring a lot of challenges, and customers look at it as is there going to be some issues now of compromising my network uptime? So those are all things that we have to look at and address when we're architecting a TLS 1.3 decryption solution.
Excellent, thank you. So I understand in previous versions of TLS, given kind of what you talked a little bit about there with the server private key and that being able to decrypt all traffic, we know that the attackers could actually capture encrypted traffic, store it on their own, and then later decrypt it once they had compromised the server and gotten the private key, and decrypt all the traffic after the fact, which is pretty frightening and certainly understandable why the community has gone to 1.3. Makes a lot of sense. So, David, what's fundamentally different in TLS 1.3 to stop our adversaries from grabbing that encrypted traffic and decrypting it later down the line? And also, kind of what can enterprises do to retain visibility on their own network traffic after implementing 1.3?
Yeah, it's a good set of questions, Scott. Chris is right. One of the big drivers for change with TLS 1.3 was to reduce the risk of capture now and decrypt later once you've compromised the server and got its private key. And the way that TLS 1.3 handles that is with fairly significant changes in the way the protocol worked compared to previous versions. But essentially, in TLS 1.3, it no longer allows any cipher suites that use RSA key exchange. And it was the RSA key exchange mechanism that allowed you to do passive decrypt when you were doing known server key, and that also allowed you to capture and then decrypt after the fact if you got that private key. So in previous versions of TLS, there were lots of different cipher suites. They all used RSA key exchange. In TLS 1.3, there's only 5 cipher suites, and none of them use RSA key exchange. They all use ephemeral Diffie-Hellman. And what that means is what ephemeral Diffie-Hellman gives you is what's called perfect forward secrecy. So for every individual TLS session that gets established, the only way you can find the information needed to be able to decrypt that session is if you are actively present between the client and the server during the TLS handshake. So it doesn't matter if you can get the server's private key after the fact and you've got a PCAP that you captured off the network, it's useless. It doesn't let you decrypt. So that perfect forward secrecy is the key element of TLS 1.3. And it's maybe worth just saying that there were some cipher suites that were supported in TLS 1.2 that used ephemeral Diffie-Hellman. So there are a handful of cipher suites that can be used with TLS 1.2 that also provide perfect forward secrecy. But there were many others that didn't. So TLS 1.2, it wasn't a big issue. You could work around it by choosing not to use the cipher suites that provided PFS. But with TLS 1.3, you don't have that option. All the cipher suites give you PFS. And actually, if you look at recommendations today in terms of how best to configure your TLS server, the recommendations are you use TLS 1.2 or 1.3, but if you use 1.2, you should only use the cipher suites that give you perfect forward secrecy. So on a well-configured server today, whether it's running TLS 1.2 or 1.3, you're not going to be able to do passive decrypt, and you're protected against the capture the key and decrypt after the fact. TLS 1.3 has been out for a while. It was released in 2018. And it's now becoming the most dominant version of TLS in use on the internet. So within an enterprise, the uptake may be slightly slower for internal traffic, but for traffic on the public internet to public websites, if you go to your bank or to Gmail or Facebook, it'll use TLS 1.3 if it can. And there are other benefits from TLS 1.3. It does speed up the connection. It changes the way the handshake works. But that also brings some additional security concerns. So in prior versions of TLS, the handshake was in the clear, and then it was only encrypted when it was passing your end-to-end data. And that meant that things like next-gen firewalls could look at the handshake without needing to do decryption and see the details of the destination server certificate and use that in policy to say, well, we don't allow you to go to Facebook, so we're going to block this session. And they wouldn't need to do decrypt to do that. With TLS 1.3, that changes in that most of the handshake is encrypted as well. So if you want to know what the destination server certificate is, you have to decrypt. And you have to be in line to do that. So there's a number of impacts from TLS 1.3, but it is much more secure than TLS 1.2. So hopefully that kind of gives an insight into it.
Yeah, fantastic. Thank you. So given all that, with the unless we kind of change our approach to how we're monitoring, if we're utilizing 1.3, we're kind of going to be flying blind, because a lot of our traffic that we utilize inside to do our monitoring won't be able to work as it does today. And also with 1.3 and requiring the decryption devices to be part of an active component within the encryption chain, given that almost all of us have multiple security and monitoring tools, they're all going to have to do their own decryption, so that if one of them fails, it could cause a cascading failure right down the line, and we all know that's not going to be good for anybody. So, Chris, how do we see the approach in monitoring enterprise traffic changing with the implementation of 1.3? What happens to the performance of the network and the applications that run on it, given all this inline decryption?
Yeah, so with this, we definitely have to rethink how we approach monitoring monitoring the network and looking at what traffic you want to be able to decrypt, and really think about how we can centralize this, because as you said, the days of just having a single device in your network at the edge monitoring, those days are gone, right? When you just popped in a firewall and said, I'm good. So nowadays customers have requirements to put in active blocking tools. So, intrusion prevention systems and DDoS and, web application firewalls. And so there's a lot of different security tools that are, need to be, actively in line. And then you also have tools that also want to get a, copy of that traffic out of band. So as we'll be talking a little later on the joint solution of Axellio also getting, copy of that traffic, you may have, customers who are running, a NDR and maybe they have an intrusion detection system. So it does get pretty complicated now that you have, you may have your router and firewall, and now you want to put in several tools that are going to be actively blocking. And then you're also going to want to take that traffic and send it to your out-of-band tools and look at a methodology to also decrypt. So when we look at that, we like to look at architecting it to, one is how do we make sure we get all the traffic and packets to your security monitoring tools, packet capture, and how do we also maintain network uptime and ensure that you have individual controls to be able to take your inline blocking tools offline or for maintenance, troubleshooting. So we look at utilizing our EdgeLens platform that is a combination of bypass taps, packet brokers, and it allows you to tap the network once and be able to send traffic to multiple inline tools as well as a copy to out of band. So when you start implementing this infrastructure, you have the ability to now have full control of Mira for the decryption side, full control of sending traffic to your inline tools like an intrusion prevention system, and then also be able to get a copy out. So if you're not familiar with a bypass tap, how it works, and we talked about passive monitoring, when we would insert a wiretap in between two network devices, what would happen is traffic would pass through the tap in both directions. So you would go from router to switch to router, back and forth, and the tap would just copy a copy of the packets flowing between the two devices. So in this case, when we start moving to an inline approach, it's a different tap technology, again, called a bypass tap. So the difference here is we would bring traffic in to the tap, and then we'll pass it through your inline device, and we do this in both directions. So what happens is it allows you to now have full control of your inline devices. So you can either have them passing the traffic through, or if you need to maintain the inline device, so maybe you have to do an update, maybe you have to do a hardware replacement. It gives you that full control that you can easily, take traffic inline and out of line. So for us, we really look at, again, how do we centralize the ability to tap the network once, be able to take that traffic and decrypt it with Mira Security, and then at that point, send it to your inline and out of band tools. So it's definitely a different approach. And my thought is that you always got to look at, let's make sure it's easy to manage. Let's make sure we can manage each of the inline and out of band security tools easily. Guarantee we get the traffic, but do this without compromising your network uptime. Because I think that's one of the biggest challenges that customers are running into is when you have to start chaining multiple tools, how you do that effectively and easily to make sure that your security tools get all the packets, but your network continues to stay up.
Awesome. That's a great setup to start discussing our joint solution here. So um, Axellio, Garland, and Mira have joined forces, and we're kind of here to talk a little bit about providing a centralized, scalable, and affordable solution to decrypt all of the traffic. It's going to allow your network analysts to perform or your network analysis and performance tools to function as they do today, which is really what we're trying to do. This joint solution ensures complete visibility. It's going to capture, decrypt, store, and distribute at speeds over 100 gigabit per second. So let's kind of do a quick walkthrough of the architecture, and we'll talk about some of the specifics. So as you see on the graphic on the screen, first, kind of let me state that this graphic is a block diagram, as our solutions can exist in both hardware and hardware form, be on-prem or in the cloud. Physical instantiations may vary slightly given, the particular network needs, but we wanted to give you a block diagram to help kind of visualize how this is going to work. So if we start at the bottom left of the graphic, first we have the encrypted traffic coming from the left and entering Garland's EdgeLens product that Chris was just talking about. This is a combined hybrid bypass tap and network packet broker. It's deployed inline at strategic points of the network to capture the essential traffic. EdgeLens will then pass that encrypted traffic to Mira's encrypted traffic orchestration, or you can see it shown here as ETO in the graphic. ETO will decrypt any encrypted traffic at scale. You'll see that the decrypted traffic is shown in green. It's being passed to the active or inline security analysis systems. But ETO also passes the decrypted traffic to the Axellio's Packet Express. Packet Express will provide a high-speed, application agnostic, open platform, and it's going to simultaneously ingest, store, and distribute these packets to your passive security monitoring tools or any other service that needs that data. This allows your existing system to keep up with any traffic by feeding them the data at the rates they can reliably ingest. And this is a key because by storing the information, it will buffer any network spikes that might come through and prevent the tools from being able to capture all of the data. By ingesting and storing the packets, it also provides a data store for your analysts to go back in time and review the packets for forensic analysis if needed. Once some of the tools might come up and show that there's something that is an issue. So by utilizing this type of architecture, we don't have multiple security tools each doing their own decryption and potentially causing that cascading failure that we discussed earlier. So Chris, what other advantages do you see in the solution, and maybe talk about some of the core capabilities above and beyond what you already discussed with EdgeLens?
Yeah, absolutely. So as we talked about, network uptime is critical, and most customers are looking to get access to multiple segments. So several things we can help with is one as stated here is the bypass tap functionality. So just to kind of make it clear for everybody. So when you look at the diagram here, you got traffic coming in, and we'll pass that traffic through the Mira ETO. And then from there, we can then also send it through other inline devices. And with that, depending on the bandwidth, so let's just take a scenario of, let's say we're tapping, 4 10 gig links, and let's just say we have, 20 or 30 gigs of traffic. So what's nice is, a couple things that we do is once that traffic is decrypted, and we send it through as this example here, let's just use the IPS as an example. And let's say your throughput on the IPS is 10 gigabit. So, a couple things we can do is when we bring the traffic in, we can then load balance it to each of the entities. So if we need, say, 3 intrusion prevention systems or 4 for some resiliency, we can actually take that decrypted traffic, and then we can load balance it to multiple intrusion prevention appliances to ensure that it can handle the bandwidth, and it can also provide some more resiliency. So maybe you have 3 or 4 IPSs in a load balance group, and any one could go offline at one time, and it would then rebalance between the other devices. So again, helping maintain that uptime. And then again, as part of the chaining, if we were to decrypt the traffic, send it through the IPS and then the WAF, same thing as maybe the WAF, the appliance can handle 20 gigs. So maybe they only have, 2 appliances in that load balance group. But it gives you, a lot of flexibility to be able to manage those devices. And again, as I always like to talk about network uptime here, because as part of the security stack, I look at Garland's job is to I always like to say the truth is in the packets, so you need to see everything. So one is we're going to make sure we get you all the traffic. We're going to make sure that you can maintain these inline devices separately. So if for some reason, we do have to take, say, Mira ETO offline to do an update, we can do that without affecting the live network. And we can do that for each individual device. So if you need to do updates or troubleshooting, so if you're not sure, the networking team says, hey, I think there's an issue with the inline block, the intrusion prevention system, we can actually take that offline and allow you to troubleshoot that. So, it allows you to take full control of your security stack, and think of us as the glue that connects everything from the network. And if something were to happen to the EdgeLens product, we do have fail-safe built in. So if for some reason someone just unplug the devices, we can have the network continue to flow or shut that down. And again, from here, we also then send the traffic to Axellio Packet Express, and again, making sure that you guys are getting all the packets. So for us, we're excited to be part of the security stack to ensure your security tools maintain network uptime, get all the packets. And we do this in a central location. So as you mentioned, Scott, right, you don't want to have to tap multiple areas and have multiple devices all doing decrypt, when we can centralize that and really make it easier for our customers to manage this and ensure that we have the network uptime along with getting the traffic and managing this in an easy, simple, cost-effective way.
Awesome. Thanks, Chris. David, can you walk us through how ETO works and does it at the very high network speeds?
Sure, Scott. And I mean, both you and Chris have got it right. You don't want to do this in a chain. I mean, chaining through devices runs the physical risk of anyone breaks the network. But actually, if you had this picture without Mira ETO there and had each of the inline tools like the IPS and the WAF do their own decrypt, then you create another chain of complexity, because each of them is dependent on understanding the certificates and keys used by the preceding device in the chain that's done decrypt. So that chain of decryption points is a bad idea as well. But you don't have that with what we're proposing here. I mean, Mira's doing the decrypt, so it's decrypt once and then re-encrypt before it goes back out to the network. And the way that Mira works is that we don't depend on port numbers to identify traffic that's encrypted. For example, we watch every TCP session that comes into us. We look to see whether a TLS session tries to start up on top of that. If it does, then we watch the TLS handshake, and we may participate in that depending on what the handshake's doing. But we, at some point during the handshake, make a policy decision on whether or not to decrypt this particular flow. And the user has very fine-grained control over that policy. So there may be traffic that you have in your network that is encrypted, but you never want to decrypt. An example might be employee traffic going off to an internet banking site. There's no need, you know it's going to the internet banking site. They're allowed to do that on the corporate network during the lunch hour, but you don't really want to decrypt that and have a decrypted copy of that transaction. So you would have a policy rule in ETO that said, for any traffic that's going to banking sites, for example, don't decrypt. So we would, make that policy decision, and then we would leave the flow untouched. It would still go from us up to the Garland edge lens and through all of the inline tools, but they would see it encrypted rather than decrypted. But for all the other flows that you do want to see inside, we will insert ourselves in the flow during the TLS handshake, and then we will decrypt all the encrypted payloads that come to us, send those up to the Garland edge lens over a TCP session with exactly the same packet header information as the original. So it's very easy to keep track of what's going on. That decrypted traffic will flow through the inline tool chain. It'll get copied off as a copy to the Axellio Packet Express, and eventually it will come back to us as the decrypted traffic. And at that point, we will re-encrypt it before it's sent out to the network. Now, a couple of points to make are that because of the way that TLS 1.3 works, the keys used for encryption between the client on the left of this picture and the ETO, and the keys that we need to use on the right of the picture from ETO off to the network will always be different. So we decrypt with one set of keys, but we have to re-encrypt with a different set to send it out the other side. I mean, that's transparent to the user, but it just makes it more complex in terms of how it's implemented. The main thing, though, with the ETO approach is that we are what we call transparent. So at the network level, we're layer 2 transparent. So there's no IP addresses on these interfaces on Mira ETO. So you don't need to reconfigure anything in your network. You just break the wire, put us in line, attach the tools to us, and away you go. You don't need to reconfigure your IP addressing or anything. And we also view it as being very important to be transparent at the TLS level. And what we mean by that is that we shouldn't change the security profile of your traffic because we're present and letting you see what's inside it. So if you look at the picture and think of a TLS session from the client to the network when we're not present, the profile for that connection, the security profile, gets negotiated between the client and the server during the TLS handshake. And that chooses what TLS version is used, what cipher suite's used, what key sizes are used. When you put Mira ETO in between the two, and we actively participate in the handshake, we maintain that security profile. So the TLS version will be the same when we're present as when we're not. The key sizes will be the same. The cipher suites will be the same. And that's quite an important thing to make, because that means that you're not weakening the security of the encrypted sessions. And there are some other solutions that do visibility into TLS that don't provide that transparency. So they would make their life easier by forcing the session to drop down from TLS 1.3 to 1.2, just because that's easier for them to process. But we view that as being kind of a no-no. If we're there, we shouldn't be weakening the security. And then, the last thing to say is we can do this, as Scott says, at scale. I mean, ETO is available as a virtual machine in private cloud or on public cloud, and a single instance can handle 5 gigs of decrypt, but you can auto scale that to handle any capacity. In terms of physical boxes, we can scale up to doing 50 to 100 gigs of decrypt in a hardware appliance with 10 gig, 25 gig, 40 gig physical interfaces on those boxes. So we're really engineered to be able to sit as that central point and do this for all of the traffic and make life easier. So hopefully that's a snapshot of what we do.
Great, thank you. On the kind of in the upper right-hand side of the graphic on the passive monitoring security side, Packet Express acts as a buffer for all the passive security monitoring tools within the infrastructure. It ensures that any number of monitoring applications can see just the traffic that they want at the speed that they can actually consume it. It can ingest 100 gigabit a second sustained with no loss of any packets. And by simultaneously being able to ingest, store, and distribute traffic, it can load balance across those analysis apps without fear of having any data dropped due to overloading on either side. The data can be stored for as long or short as need be. It allows you to rewind and replay the traffic for repeated in-depth forensic analysis. So you can kind of think of Packet Express as a DVR for your packets. Rewind, replay at the speed you want, higher, faster, slower, doesn't matter. And it gives your cybersecurity analysts immense power to be able to track down anomalies in the network, and even do things like test out possible security mitigations prior to a larger release to the rest of the network. Packet Express also has the ability to compress and encrypt the data as well. This ensures that your information will be protected after it's taken off the wire by EdgeLens and decrypted by ETO. So your analysis applications can then use a key accessible just to them, protecting the data until it's no longer needed. Every network's going to have a different dwell time in terms of how long they want to keep that data in Packet Express. But being able to encrypt in there, making sure that it's not a repo that someone's going to come try and attack, gives you a lot of flexibility as you build up your network architecture. So we're starting to run a little bit short on time. We wanted to leave a little bit of time for 5 or 10 minutes here or so for questions. So Chris, let me flip it over to you for any last comments.
Yeah, no, definitely, Scott, David, as always, great talking to you both, and really enjoy the session today. And yeah, it's an exciting topic. A lot of people, are looking at ways to, be able to monitor their security stack and get decrypted data to their tools. So, anybody, watching the webinar or wants more information, obviously, as seen on the screen, reach out anytime, and look forward to speaking to people about this topic in more detail.
Great, thank you. David, any last minute comments?
No, I'd echo Chris's comment. I mean, if you've got questions, reach out to us. We're always happy to talk. And I mean, we've a few minutes left. If there's questions now, then we might be able to deal with some of those online. But yes, I mean, if you go to Mira Security's website, there's a lot of material, white papers, videos that walk you through what we do and how we do things. But at the end of the day, I'm always available on an email if you've got a question.
Okay. Well, gentlemen, thank you for your time and insights. Really interesting. You guys are incredibly bright and intelligent on this stuff, and I think can help the customers a lot with trying to figure out, a very important decision as people are building up their networks in terms of whether to flip over to 1.3 or stick with 1.2. And great discussion. So let's open it up for any questions.
Great. So Scott, we did get a couple questions. Looking through, this one is a little bit of a multi-part question. But David, you're definitely going to want to start here. So picking up on your point about selective decrypt, how do you envision the Mira ETO to accommodate the encrypted client hello extension to TLS 1.3 that encrypts the SNI data?
Okay. Well, we could spend a good hour talking about encrypted client hello and the pros and cons of whether it's a good thing or not, but this isn't the venue for that. Encrypted client hello, for those who don't know the details, is a proposed extension to TLS 1.3 that's being discussed and worked on in the IETF TLS working group. And it's, as the question says, it will encrypt more of the handshake to make it even harder to figure out what's going on in the network. In fact, unless you can figure out ways to address encrypted client hello, you won't be able to know where any traffic across the network is going, at least as long as it's behind a CDN network that's providing an anonymity group. At the moment, the way we handle that, it's not deployed fully yet, and it's still being worked. It's not approved yet in the IETF, but that will happen, I think, fairly soon. At the moment, we would, and most of the customers we have would prevent its use in an enterprise network in the same way that most enterprise networks prevent QUIC being used. And that's doable for traffic coming into your network because you control your own servers and they can choose what features are and aren't used in TLS. If it's outbound traffic, then it depends on the server that you're going to, but you can choose to indicate that none of the clients in your network support encrypted client hello, which means the external server, can choose one of two things. It either won't allow your connection or it will fall back and use TLS without encrypted client hello. So that's kind of where we're at with that. But it is an ongoing area that we at Mira spend time looking at. We do track all of the activity in the IETF and the new developments and make sure that we're ready for them when they actually get deployed for real. So I hope that partially answers the question at least.
Great, thanks, David. And then one more question, because I think this won't be a shorter one to answer. Can the overall solution between Mira, Garland, and Axellio handle an inline tool that may change the IP or MAC address?
Not from a Mira standpoint. So we need to see the source and dest IP and things that comes back from the inline tool be the same as the address that we sent the traffic to. So it's a transparent inline tool rather than, for example, a proxy that might be terminating and re-originating with totally different IP addresses. Does that help?
I think so. We had a couple other questions, but I think those are going to, take much more in-depth, lengthy answers. So I would say it makes sense to take the rest of those questions offline and we'll answer directly. And just keeping in mind everyone's time and availability today that we have used the full length of time proposed for the webinar.
Okay. Well, as you can see on the screen, we've got our email addresses. please reach out if you've got additional questions. Sounds like we've got some tough ones that are going to take a little bit more time. We'll be happy to get back to you on that and maybe set up a specific call to talk through those. And certainly understand that we'll reach out to everyone that sends in a question, either individually if there's a question that's directed at one of the products that are listed here, or if it is a solution related one, you'll get something from one of the three of us. So thank you again for your time, David, Chris. Thank you as always. Really appreciate everyone's time, and hope everyone has a great rest of the week.
All right, great. Thanks, Scott.
Thanks, guys.
Thanks, David. Thanks, everybody.